so much for coming along tonight. Unfortunately, no moon visible, which is a bit of a pity, but possibly not totally surprising. Tonight we're celebrating Yuri's night. What I want to do is to talk a little bit about some of the things that we've learned, and in relation in particular to a couple of the things to do with the junior science curriculum, but whether or which you're a teacher or not, it hopefully will be interesting. But I'm going to try to layer it into what might be the sort of things to think about if you were doing this within the bounds of a curriculum. And if you're not, then don't worry, hopefully you won't even notice the difference. Okay, so I'm hoping it's seamless irrespective. This is a couple of points which I think are interesting. This is about a sort of a 40-45 minutes talk, or if everybody has fallen asleep before 45 minutes, we'll finish early, but hopefully that won't be the case. So, but you could go on for hours on this type of thing, of course. So it's inevitably going to be some things that I think are interesting for tonight's talk. If I was doing a talk next week, or we're having a chat next week, obviously I would try to change it. But also, if you have thoughts, please feel free to add them in at any point. Okay, so so celebrating Yuri's night. So there's a couple of things, and how many of you are doing this from a teaching perspective? Are. Hey. Okay, so don't worry that you're not. The only reason is that there's one scary slide. Okay, so if you're not doing this from a teaching perspective, you might think, oh, am I in the right place? And actually you are, so don't worry about that. But essentially, some of the things that the junior cycle asks, and by the way, we make the slides available to everybody subsequently. Doesn't mean you can't take notes. Obviously, I'll hopefully say some things that are of interest which aren't on the slide. But since I'm not going to be reading the slides, with the exception of maybe this one, but just to note, that we were kind of thinking a little bit about how scientists work, about the role of science in society, a little bit on some of the benefits, but that's a very broad thing. Even from the point of view of space, that's very broad, so a couple of pointers, and a couple of things really to get people thinking about it, whether you're young or not, whether you're teaching or not teaching, and some of the current hazards, because this is one of the specific things that space imposes on us, but also then the opportunities that it does. So, for those of you who are old enough, I think none of us here, Sputnik was kind of what kicked it all off in 1957, and then just 4 years later, the man for which Yuri's night is referenced, Yuri Gagarin, was the first person in space. He did an orbital flight, and I'll explain to you in a couple of minutes what technically that means, not really in technical terms, but what that means, because that kind of gets interesting when we talk a little bit about space tourism, so which I'll come to in a little while. But my dad used to always say that he was the bravest man. My dad's 92, because he was like the first to do this, and what would you find? I mean, there was obviously the idea if you'd be weightless for 90 minutes and so forth. And the obvious thing about when you're up there, how do you get down? It's difficult going up, but it's somehow controlled. But when you're coming down, the Earth is only going to do one thing, that's bring you downwards. So Yuri Gagarin started the race for people to go into space. What's happened since then? That's kind of what we're going to be talking a bit about tonight. Because of course, a few years later, 8 years later, we landed on the moon, and this year is the 50th anniversary. You're going to hear a lot about that. So I'm not really going to talk about moon stuff tonight at all. I'm going to refer to the moon in a second. I'm not really going to talk about the moon landings. Now, I was old enough to remember the moon landings. I think it's one of the most amazing achievements, period. And it's the most amazing, one of the most amazing, simply because it's the first time in the history of our planet, which is 4.5 billion years, that somebody walked somewhere which wasn't the Earth, if you think of it in those terms. First person to stand on an object which was not the Earth was Neil Armstrong. For me, that's a special thing to be. First person to not be technically completely tied to the Earth was Yuri Gagarin. So, a couple of things about observations and deductions. So, if we look, for example, at objects in the sky, and I hope you can kind of see it here. You can see the moon or Mercury, and they look quite similar. That's one of the first things I noticed, that the moon and Mercury look quite similar. If you look a little bit closer, they look still quite similar. They show signs of these objects, these craters. So something causes these holes. And I remember when I was young, there was a discussion, were they volcanoes or were they impacts? And that changes your model of the solar system hugely. Was the solar system somehow put together in a benign way, and then these volcanoes threw out material, or was it a very violent start to the process? So if you're digging holes in things that are hundreds of kilometers across, that's a pretty violent start to your solar system. Maybe it was, maybe it wasn't. Today, without going into all the details, we now know that these were caused by bombardments. But this is also an asteroid, and an asteroid is effectively a lump of rock that didn't make it into becoming a planet. And you see all asteroids that we see have bashy things in them as well. They've got holes in them, they've got craters. So in the past, at some time, just by looking at these diagrams you can't tell when, but sometime in the past, there was a lot of impacts happening. Now, today we don't see a lot, we don't hear of people getting hit by meteorites, we don't see big holes being generated on the planet. When we look at the moon, we don't see lots of new craters. So it looks like this happened sometime in the past and it's kind of stopped. So that's a deduction you can make by just looking at some of those pictures. If you look a little bit closer, you can figure out a little bit exactly when they occurred. So if we stick with the idea of the moon, then the fact that it's there makes you think, how did it get there? So I just mentioned about craters, and there's a couple of different theories which don't work, but just wanted to introduce them to you. So if you imagine the moon, could the moon have existed and been captured by the Earth? Well, it turns out that if you have a big object like the moon that has to be passing by the Earth, and gravity of the Earth sort of captures it, the chances of that happening are really small. It's like playing the lotto, the Euro Millions, but actually with not even all the numbers. So the chances of that capture happening are incredibly small, so that's unlikely. The second possibility is that the Earth, when it was very young, was spinning so quickly that it threw the moon out. You can look at that, but actually, if the Earth is spinning that quickly to begin with, you don't make an Earth. It'll never come together, because as soon as it tries to pull itself together, if it's spinning that fast, it throws itself apart. So there's two possible theories, they're not the only two, but if you look at it a little bit more closely, they don't work. Now, you can't necessarily easily do this in school with an example, but you can get people to think about, the kids to think about different possibilities as to how you might build an Earth-Moon system. What we now believe to actually be the way things happened, because when we try to do the calculations, this works for us, is that about 4 billion years ago, an object, the Earth was this ball here. Talk a bit more about it in a few minutes, because this was a really nasty Earth early on. The Earth today is lovely. It wasn't at that stage. And it got hit by an object roughly the size of Mars, just fast enough so that it gouged a big load of material out of the Earth, which went up into orbit, and then it went around this way, and that then reformed as the moon. So actually, one thing I always like to say is, when we went to the moon, or when we go to the moon, we're actually going back to the Earth, because the moon was originally part of the Earth. And there's all sorts of evidence to show that this model works. And by going to the moon, we can take rock samples and figure out, do the rocks on the moon look like the sort of way you'd expect if this happened? And it turns out they do. So this model, which is the giant impact theory, okay, it's got to be giant, seems to fit the model. Yes?
The impact or stay part of the Earth, or did it
No.
go on?
Yes, in part. A little bit of staying part of the Earth, a little bit of thrown up into space. So it gets mixed between the two. Yeah. What interestingly, one just commented about it, and we could talk at length, and it would be interesting, but I want to cover a couple of things, and I don't want, as I said, to put you to sleep. So on that basis, the Earth at the core would have had iron in it. When this impact happened, that the material that was thrown out wouldn't have been the core of the Earth. So actually, there's not much iron on the moon. So if you go to the moon doesn't have a lot of iron, which is kind of consistent with this. If this impact had smashed the Earth into complete pieces, you'd imagine there was as much iron on the moon as you would on the Earth. So we think that this only ejected sort of the outer layers of the Earth. But there's an interesting observation. People say, well, why do you measure iron on the moon? Who cares? Well, actually, iron on the moon tells you that this helps to tell you this model works, which helps to tell you where our home planet is from. Why is this also interesting? Well, if you look, we think that in the early days, the Earth was rotating vertically. But when we got whacked by this object, which is called Theia, Theia, it also tilted the Earth's axis by roughly 23 degrees, which gives us our seasons. And actually, the Earth, Moon, and Sun, if it was in the picture here, combination, give us the tides. This is hugely important for life on our planet now. So actually, this way that the Earth was made has influenced the type of way life has evolved on the planet. We know that, for example, the movement of the plates on the Earth are helped by the squishing of the gravity, or the pulling and pushing of the gravity of the Moon and the Sun. And that transforms the Earth's landscape over millions of years. But that turns out to have a big impact on life. So by looking at the Moon, by looking at these impacts and so on, and thinking a little bit more about it and going back to the Moon, we can actually tell where our Earth came from. I think that's pretty cool, that we can actually figure that out. So all the possible scenarios, we can reduce them to this particular one. Impacts, by the way, go on. I mentioned we don't see a lot of them, thankfully, but they do happen. This is back in 1994. If you look at these few dots here, then this is a comet about to crash into Jupiter. It's called Comet ShoemakerLevy. There was two amateur astronomers discovered the comet, and this is it breaking up as it moves. So this would have started out as one object, and then the gravitational force of Jupiter ripped that apart. And then if you look here, these two sort of black things are where some of those cometary debris crashed into Jupiter. And actually, if you look at it in infrared, this is the moment one of them hit the planet. So this is the planet Jupiter here. This is one of the fragments of Comet ShoemakerLevy. And you can actually see in infrared that it's heated this part of the planet. And that lasted for several days, actually several months, but it eased off. If that had hit the Earth, for example, that ShoemakerLevy, if it had hit Dublin, Cork, London, Paris, whatever, actually, then that would have destroyed those cities and so on. The good thing is that in general, Jupiter, which is very big, is inclined to pull the small stuff towards it, and the Earth doesn't. So the chances that Jupiter gets hit by a lot of stuff, the Earth gets hit by very little. Sometimes there's an advantage in being small and unassuming. So if you're big and loud, you attract attention to yourself, which isn't always the best thing. And that brings us on to this idea of threats from space. So one of the things about the Junior cycle is about the kind of threats from space bit. So let's not get people concerned, because actually one thing you can say in general is that the likelihood of you seeing anything of any importance, any scale, any size happening in your lifetime now, at this time, is almost zero. If you were on the Earth 4 billion years ago, it would have been a really nasty place. You would have been ducking meteorites all the time. But 4 billion years on, they've all hit something, and they're no longer there. But nevertheless, if you look here, this is the Sun. So you got Mercury, Venus, Earth, and Mars, and then you've got the asteroid belt here in green. So the red things are objects which, on their orbit around the Sun, pass the orbit of the Earth. Obviously, if you're passing across the orbit of the Earth, there's a chance that sooner or later you'll hit the Earth. So these are what we call near-Earth objects, Earth-crossing near-Earth objects. Of course, this is not to scale. It is, each of these dots is many times larger than the actual size of the Earth. So it gives the impression that, oh my goodness, it must be inevitable. But actually, we're a very small target, and these objects are very small. Nevertheless, they're there, and there is the potential for them to impact the Earth. So in a minute, I'm going to explain to you why that has spawned, or how that has spawned some ideas to try to stop that. Because an impact might be rare, but if it happens, it can be really catastrophic. But interestingly, only last year, you might remember that an object called Oumuamua, I probably got that wrong anyway, so I'm not going to say it a second time, came into our solar system. Now, you may have heard about this, but if you didn't, it's even better, okay, because you're going to hear something that I think is very exciting. So here's the Sun and the planets. Now, the planets in general all are on the same plane. So they all go around like on a plate. Comes in from a high angle and heads off out. And if you do the calculation, it doesn't come from the solar system. It comes from somewhere else. So this is not a picture. This is not like the black hole picture, which is a picture, and that we saw a couple of days ago. This is an artist's impression of what we have some vague thought this object might look like. We think it's long and cylindrically, cigar-y shaped. There's a lot of discussion about its actual shape. But what we do know is its trajectory tells us it came in from somewhere else and headed off. So what I think is really cool about this is probably going on all the time. We just don't see these things. But this object, if you could have been sitting on it for the last 4 billion years, or maybe it's been around longer, because our solar system has been around 4 billion years. The universe has been around 13.7 billion years. This object could be 10 billion years old. It may have been wandering the cosmos for 10 billion years. So if you could have sat on it, goodness knows what stories you could tell. But one of the stories you could tell is you come into this system where you saw these different planets. Maybe as you come in, you saw that one was inhabited, and then you head on back out, never to be seen again. So the sun doesn't capture this. The gravity of the sun isn't strong enough, so this thing heads back off out into space to wander. Maybe eventually it will get captured by some star, probably inevitable, but that could be so far in the future as to be effectively irrelevant on all reasonable time scales. But what this is the first time, and it's only happened last year, that we've actually seen an object which doesn't come from the solar system. So all these objects here we think got formed while the Earth was being formed and while the Sun was being formed. They're all part of our solar system. This thing came from some other solar system. Really fascinating to know which one that might have been. One of the things that NASA likes to talk about is big events like Earthsterilizing. So when I mentioned about the reason why you don't want to worry kids, because kids, of course, depending on what age, can get very worried very quickly, and saying this is unlikely to happen to you doesn't always work. I remember a sister of mine was frightened by lightning, and my mum asked me to reassure her. She was in her home, so I phoned her and said, "Ursula, the chances of lightning hitting you is about 1 in 10 million. Now I was making it up. She said, "There's a chance." And I learned at that moment that a 1 in, if somebody is worried, that's all they hear. It's a non-zero chance. The chances of something large hitting us at this stage in the development of the Earth, it would have been very common early on, is very small. However, if it does happen, it does very nasty things. It is inevitable that at some point, it might take a billion years, it could happen in a few years' time. I mean, we really don't know when these things happen. So it probably is a good thing for us, and I'm not going to talk a lot about it tonight, but it's probably a good thing for us, is to develop technologies that will push one of these things out of the way when we see it. Probably a lot of us seen Deep Impact or Armageddon or whatever it is and so on. There's a lot of truth in those movies, actually. The movies, because in a way all you're doing is you're taking a big lump of rock and you're throwing it at something. And if you've ever done this at a window or something, you know it goes badly wrong. So just throwing things at other things at high speed is a bad thing to do in general. And so it's interstellar billiard balls. This happens. Of course, we know that it did happen in the past. The key thing here is the dinosaurs didn't see it coming. And the question here is, what's our excuse? Because we're the first people, we're the first species that we know of. Put in a caveat about that in a second. We're the first species that we know of on this planet which has developed the capability to protect ourselves from something that destroyed the dinosaurs. And we know that this has happened a few times in the past, not just the dinosaurs. The dinosaurs were quite evolved, but a couple of 100 million years prior to that, life was much simpler and it got almost wiped out. Hence the term Earthsterilizing, which I think is a great phrase. But incidentally, on the sterilizing, we now think you pretty much can't sterilize a planet. So you can wipe out you and me pretty easily, unfortunately. Getting rid of bacteria or viruses or things like that is almost impossible. It's really difficult. There's some life forms that are really so resilient that it's almost impossible to get rid of them en masse. So even if you broke the Earth into little pieces, there are some life forms that will survive. In order though to understand a bit more about these asteroids and to understand can we push them out of the way, there is a mission which has been launched shortly called DART. And DART will have two parts to it. It'll visit this Didymos and Didymo, which I think is just a wonderful name for an asteroid. It's an asteroid that has a moon, so clearly Didymo and Didymos. I guess that was obvious. But what's interesting is although these are tiny by comparison, there's just enough gravity for Didymos to hold on to Didymo. So it's a combination of European and American project, which is to basically fire a payload, hence why it's called the DART, at this and see if we can move it just a little bit. So the idea is, will it break up? Will it move as much as we think and all that? So it's testing the technology for actually moving something. If this is moving around this, then it's easy to see the effect. Because let's suppose it ordinarily takes 10 days to go around. I don't know what it is, I don't remember. So it doesn't really matter whether I remember, but let's suppose it takes 10 days to go around and it's at a distance of 10 miles, so 10 kilometers. Well, if it now takes 11 days and it's 9 and it's at 12 kilometers, well, now you can figure out what the thing is. So if something is going around something else, you can measure the impact of the impact more easily than if it's just kind of floating free. So this is a very smart thing to do, is to fire something at an object going around something else. Of course, that's to scare us all, our socks, but not all collisions are bad. So first of all, going back to the Earth 4.5 billion years ago, so this is clearly not a picture of the Earth 4.5 billion years ago, but we know the Earth 4.5 billion years ago would have gone to what sometimes is referred to as the Hadean phase. And essentially we think, well, we pretty much know, that the Earth would have been exceedingly hot. That would have evaporated all the water. So the early Earth would have been devoid of water. Now, apart from the fact that it was too hot for life, it would have also been devoid of water. So when it cooled down, if you've no water to start with, you still know water when you're cool. But cooling down doesn't generate water. So where did the water come from? So it's a very important question, because we know that all life forms on Earth, and I'm not a biologist, so every time I say this I think somebody's going to tell me this is wrong, but I always try to double check it. So I can see smiles in the audience already. I think, oh, I could be in trouble here. But my understanding is all life forms on Earth require water. Not all require oxygen in the free form, but they all require water. So water is a fundamental thing. So it's clearly an important question. So if we actually ask where did the water come from, we're asking how did you and me come to be? Well, I mean, obviously it's apart, but it's really important to know this. So we know, we kind of get an idea of the Earth, where the Earth came from, this collision, and the Moon. So where did the water come from? Well, this graph is a bit busy, but actually once I show it to you, it's actually quite straightforward. So if we look at water, and this might be a little bit too, depending on what age you're talking to, you don't have to use all of this, but just bear with me for a second and maybe try to see whether it makes sense. Let's in any case understand it together, and then let's figure out whether it might be useful. It would be a separate question. But the water in you is 2 hydrogens and an oxygen. We know that, H2O. Some of the hydrogen is hydrogen, so it's a proton and an electron going around it. Some of it is deuterium, which is a proton and a neutron and an electron going around it. Now, the ratio of deuterium to hydrogen, so D to H, is a number. What do I mean by that? Well, on the Earth, it turns out to be, this looks like roughly 1/10,000. Okay, so it's a log scale, which makes it slightly more difficult, but it's roughly 10 to the minus 4, which is a 10,000. But this is the amount of, this is the ratio. All you really need to know, even if you don't know what the number is, this line tells you the ratio of deuterium to hydrogen on the Earth, the water on the Earth. So if we measure the ratio of deuterium to hydrogen in lots of other objects, we can see and plot them, we can see what we get. So if we do it for asteroids, you see a lot of them actually are along this line, so the same value. So that's interesting. If we look at objects like Jupiter, way different. Jupiter's way down here, Saturn's way down here, Uranus, Neptune, they're way off. The ratio is different. So it looks like the water on them didn't come from the same place as the water on the Earth. And if we look at comets, because when I was growing up, we always call comets dirty ice balls. And there's just the assumption that the ice on them was what gave us the water here. Turns out that's not the case. If you look at these comets, but if you look, they're all a bit up here instead of down along here, whereas the asteroids sit really nicely. Now, if you're not familiar with the difference between asteroids and asteroids are kind of big lumps we think of them as big lumps of rock. We think of them mostly between the orbit of Mars and Jupiter, the asteroid belt. And when I was growing up, they were kind of interesting, but not. They were bits of leftover the solar system, who cared? Comets, however, had big tails. They were fascinating, they were visible, they were portents of all sorts of terrible things to come or whatever. It turns out that comets are fascinating, they're big and blah, all the things I just said a second ago, except for the portents bit. Alright, that was not true. But other than that, they don't seem to have played a particularly significant role in our planet, whereas asteroids do. So asteroids crashing into the Earth would have brought the water back after the Earth cooled. So those impacts we saw earlier on are critical, because if impacts didn't happen, we would have vaporized all the water and nothing would have brought the water back, and I wouldn't be talking to you tonight, and we wouldn't be here looking at the universe around us. So impacts can be good. In fact, impacts were crucial. The right ones. The wrong ones, less interesting. The right ones, fantastic. So, moving on, bad, good, and then the type of things we do. So, if we look at risks that we make, and also some of the other naturally occurring, let's just think about this for a second. I'm going to use the word space junk. So, we launch stuff into space, we know this now. And when we do that, stuff gets left in orbit that isn't really doing anything very useful. So we call that space junk. So it could be, for example, the bit of the rocket. You know, when you send up to something, the rocket kind of has to fall apart. Not fall apart, it's intentional. But it breaks itself up to allow things to be ejected and so on. But some of those stay in orbit. But until they come down, they're floating out, not doing anything very useful. They can bash into each other and cause more. Or an old satellite. You kind of think, I remember when I heard this first thinking, old satellites, yeah, but surely if you spend all this effort to put a satellite up, you look after it. But at some point, people just stop looking after them. They just switch them off and walk away. Kind of sounds weird, but that's what happens. But there's millions of pieces of different things. Now, the number of old satellites is pretty small, okay, so that's not the real bit. It's this other stuff which is really important and unfortunate. So, but it is going to get worse, and I'll come to that in just a second. Nevertheless, here's a graphic showing you space junk. There's an estimated 170 million pieces. There's clearly not 170 million dots here. These are some of the larger ones, maybe 10 centimeters across. What you can see, I think, is a couple of interesting things. And this is where if you're asking a group, in a class, you know, what do you see here? I think we all can see it as a kind of a ring bit here. We can certainly see there's a lot going on close to the Earth. And then there's some bits and pieces which appear to be further away from the Earth. So this actually kind of tells you that most of the satellites and most of the debris stay relatively close to the Earth. There's then a bunch of satellites that orbit the equator. They want to sort of sit over the equator of the Earth, and they want to be far enough away so that they go around the Earth once in 24 hours, because that means the Earth has turned once in, which means they appear stationary in the sky. So the orbital period of what we call a geostationary is stationary from the perspective of geo, the Earth. So if you look at this diagram, you can see, this is real. I mean, these objects move around, but this is a real snapshot. There's a website, I don't think I've actually included on one of these view graphs, but if you type in space debris tracking or something, you'll find it. It's a US one. And they show you day to day what's where. And you can zoom in and so on. Here's the International Space Station. This is a chip. The International Space Station actually uses multiple layers of glass because we knew this was going to happen. This is a bit closer up. People get very concerned with the International Space Station, and there's two reasons at least for that. First reason is it is the most expensive experiment. It's about $100 billion now at this stage. It's a lot of money. Think of how many years you'd have to work. So the second thing is it's got people on board. And if we're going to keep the human element of our space endeavour going, we can't be having people die in space. It's just, it means that we'll stop doing it. So we have to be really careful, and I know that's we should look after people anyway. When it comes to the space thing, you have to be really careful. So we try to make it as careful as possible. The International Space Station, about 3 times of the year, moves itself. Not in any magical way. It gets moved in order to avoid space junk that people can see is coming its way. So about 3 times of the year, that has to be done. You can't duck and dive everything, and sometimes when you don't duck and dive something, here is a picture from what's called the Sentinel 1. So Sentinel is a spacecraft which is designed to look at the Earth, to take pictures. That's not the particularly interesting point here. There was a camera put on board the Sentinel 1 to see if the solar panels, these are the solar panels, had opened up. That was its only function. This is not the actual camera that does all the fancy work. This is just a camera to see, because when you put it into the spacecraft, you fold everything up and then you unfold it in orbit. But this camera nevertheless turned out to have a useful function, because the spacecraft, the operators noticed the spacecraft moved of its own accord. And they thought, okay, is it our propulsion system has kicked in or whatever, accidentally. And when they looked at the camera, and I hope you can see it, in that circle there was a big dent. And that was a piece of space debris, who knows where it came from. Who knows? It could have come from another solar system, it could have come from the Earth. We don't know. But the thing is, it did some damage. This is a map of the various places on the Earth where bits of space debris, including things as big as this, have fallen. This is, by the way, these aren't meteorites. These are things that you and me, or at least our species, have thrown up into space. And they've fallen back. And you can kind of see that there's a couple have come a little bit close to where we are. But you can actually kind of get a sense that if you look at the map, some things that are surprising in a way, and not surprising, the US, because they launch a lot of stuff. But there's a couple of places, if I just go back, where I think it's a little bit surprising. There's a lot going on in Southern Africa and a lot going on in South America, which I don't fully understand, I have to admit, why that's the case. Europe, you can actually see a line like this. And one of the reasons for this is a lot of the Earth observation satellites go, if you like, they go at an angle. Technically they're going in a straight line, but the Earth is rotating underneath them. So the net effect is they go at an angle. And if you look at this line along here, then there's a series of different lines you can imagine. But you can actually put them in what's called a sun-synchronous orbit, so they appear to do the same line every time. And the net effect is, if you're traveling over, like anything, if you're traveling over space more often, you're more likely that something bad's going to happen. Anyway, nobody's been ever hurt but therefore by definition killed by a piece of debris, not even from outer space that we know of. So nobody's actually been killed by a meteorite in the 100,000. Well, I guess Homo sapiens have been recording this for what, a couple of hundred years, I suppose, maybe 500 years. I don't know. Maybe even imagine a couple of 1,000 years. But anyway, so some impacts then of these things are intentional. So the Chinese blew up a satellite back in 2007, and some of you may have heard that just a few days ago the Indians decided to blow up one of their own satellites. So they just on March 27, this is an example of the missile going up, and what they were really just basically trying to show was we can blow up stuff in space, so don't mess with us. So there's a whole political thing here obviously going on. Unfortunately, and I might just backtrack for 1 second, you can see what happens when you blow something up. Lots of debris. In fact, you can see lots of debris here and lots of debris here. But you can actually, this is because it's going around, it looks like it's all, but it's actually all distributed. I hope you can see the red dots overall. So it looks a little bit false. But this is like 3,400 fragments. So 1 minute there's two objects, the satellite and things going to hit it. Next minute there's 3,400 smaller bits. This is really not great, but in some cases actually you've accidental. These two satellites just bumped into each other. Which I think is really bizarre. But nobody. This was an old Russian satellite, which the Russians had stopped working, so they forgot about it. Nobody was tracking it, and when the guys put up these Iridium satellites, which give us lots of the telecommunications, your TV stuff, and all the rest, and there's quite a few of them now. I think there's 64 of them up there at the moment, these particular ones. This one just bumped into this, and this is what happened. This is the debris tracked. A mere 2,300 fragments. So we can, unfortunately, pollute space as well as polluting our own planet. We're not great at this. However, once somebody's polluting, somebody else is hopefully trying to clean up. So there are efforts to clean up the debris. They're at their very early stages. To me, I think these are two interesting artist impressions. These are artist impressions. If you were to imagine the approach by two different cultures as to how you would clean something up, would you carefully collect it and return it gently, or would you vaporize it? So if I was to say, and I've already given the game away, think of two states, the United States of America and the Japanese. Which one do you think would be which? But I've already said Japan on this one. So the Japanese have this kind of, let's do this in a sensitive way, and in fairness, if you vaporize things, really vaporize it, it's actually a good way of doing things. But clearly if you're vaporizing things, you can also vaporize other things. So you can kind of see there's a thinking behind the two. There is an interesting possibility of ecologically friendly spacecraft. So spacecraft that after the end of their lifetime, you redirect them, bring them back down and burn them up basically completely in the Earth's atmosphere. The company or whatever that manages to do this is going to make a lot of money. Incidentally, some of this is possible. Some of the electronics, not so. I mean, the electronics has stuff in it which is inherently, these heavy elements. And they don't burn up. I mean, they get hot, but they don't burn up in the strict sense. And there's really no way to destroy them, not under the sorts of energies that you can generate with this. I mean, burning stuff in the atmosphere doesn't generate that enough energy, but by a country mile, to actually destroy things like I was going to say uranium, but I can't think of it like even silicon or whatever in your stuff. Silicon is actually mostly it's inert, but if you ingest it in reasonable quantities, it's poisonous. Coming back to through the Earth's atmosphere it might break bonds between two silicon molecules or two silicon atoms, but they're still silicon atoms. So it doesn't really solve any issue. So the future uses of space. So, what are they? Well, this is where we're at a really interesting, exciting time. So, for those of you, those of you who aren't talking to students, this is a really good time. And by the way, those of you who aren't, the two girls that I know here, this is a really exciting time to be excited by space. And I'll explain to you in a couple of minutes why this is the case. But first of all, just to explain to you a couple of terms, very simple, they're probably all totally obvious anyway, but just for the sake of it. So, this is the Earth, it says here. Here we have what's called low Earth orbit, and we put up small satellites called CubeSats. I'll explain to you very briefly what Space 4 and New Space is in a second. But this is satellites which are a few hundred to a couple of thousand kilometers. This is where most of the satellites are now going. This is the geostationary ones, very far out. This is traditionally where we put a lot of stuff. So traditionally TV, and it's still the case, you know when Brian Dobson talks to somebody in Brussels and he says something and they look like they're being ignorant because they're not responding. We all know now they're not, because we all know they're waiting to hear Brian finish. So that delay is actually because they got to send a signal right up to this satellite, come back and so on, and the satellite has to process it, etc., etc. So this is okay under some circumstances. But for example, if you're betting on the markets, that's too long. If somebody else can do it quicker than you, they can see what the market is doing, and they can say in the next 10 seconds the market's going to go up and they can do all this hedge betting and all that. Something I have no real concept of what it is. All I know is that lots of people make lots of money by doing nothing very constructive, but you got to have money in the first instance to do it. And the other thing you have to do is to know what's going to happen to a graph. That's what I really do look at it. You have to know, is the graph going to do this, this, or a combination of the three, and you can make lots of money just being able to predict that. If you know before the person next to you that's doing this, that gives you a competitive advantage. So actually being close to the Earth for all sorts of reasons, financial but all sorts of other reasons, gives you a competitive advantage. Some of you may have heard this before, but I also think it's interesting. Galileo, when he invented his telescope, one of the things he used it for was to look at spice ships coming over the horizon. He could see them before others could see it. So he could say to the merchants, I'll tell you when the spice ships are coming, or I'll sell you a device that will allow you to see the spice ships. You'll know what the price of certain spices are going to be, and they could bet against it. So he was a businessman as well as everything else. So we call this low Earth orbit. Sorry, this is annoying when I do go back and forth. This is low Earth orbit. So why is low Earth orbit of interest? So first of all, very quickly, if you want to go low, you don't have to put much energy. Hope that's reasonable. So that's cheaper, basically. I use the word latency. If you're low down, then the time it takes for me to talk to you via a small satellite that's low is shorter. This is really important for autonomous vehicles. So in the future, when we're all going to be obviously not driving autonomous vehicles, because by definition we'll just be sitting in the autonomous vehicles, the driving will be done partly by sensors that are looking at the local environment and partly by global positioning from satellites that are only 150, 200, maybe 500 kilometers above you, but not geostationary. If you have a small satellite, then you need less power. If you need less power, you can make them smaller. If you can make them smaller, it's cheaper to send them up. So if you can see, it's kind of a virtuous circle. If I send it lower, they can be smaller, so it's less expensive for me to send it, or I can make it smaller, and therefore, but I just say that twice, then I can send it up. But I can also do something, if I can make them smaller, I can bundle a whole bunch of them. I'll show you that just in a second, onto the one launcher. So traditionally you might put one big satellite and one small one. Now we're going to put 60 or 100 on the one launcher. So this makes it much less expensive. So everything makes it less expensive. If you like, everything conspires to make it less expensive. What are the disadvantages? Well, we need. Actually, I just realised that was like as if there was a problem here. This is, and it isn't. It's just an observation, so I have no idea. I think it's exciting, so I don't know why I said it. But if you're low down, then you're going to pass over somebody in a couple of minutes. Of course, the problem is if I'm talking to you on the phone and there's only one satellite, then I have to wait until that comes around. So it's a very staccato conversation. So what I need to do is have, as one goes over you, another needs to be following behind it. So we end up with these constellations. So you end up with lots of small satellites instead of just one big one. So that poses some challenges. This is a typical CubeSat, we call them now. This is the sort of size of satellite. Some of them are a bit bigger than this, and you can still have very big ones. The American military ones are still huge, for example, but they're getting smaller. And in fact, this here is stuck on the side of this, and this is its own satellite, stuck on the side of this satellite. Now it's not actually stuck there, but this fits on there. You can see the scales. So this actually will work completely independently. This is just a yoke that holds it, so to speak. This thing can communicate with the ground. So you can imagine holding in your hand something that will be able to communicate. And if you think of your mobile phone and the size of the camera on that and how small that is, you don't need very much space anymore to do this. So you can put a very nice lens on this, whatever it is, and take some pictures. Is that commercially useful? Well, that's a separate question, maybe for some other time. But actually, we see schools already launching these type of satellites. And we're probably going to see one launched from Ireland. My guess is this year. So we use this phrase, I mentioned earlier, new space. I'm just keeping an eye on time. But new space, we use this term new space. So old space or traditional space is the likes of NASA, putting up big rockets and it costing you half your GDP. New space is all about small companies, small things that are inexpensive that you put up very quickly. They use a technology which is used in other disciplines called COTS, components off the shelf. So you basically buy, let's say you take a mobile phone. Companies have done this. They take a mobile phone, they strap it to the thing, and they send it up. Genius. I mean, the mobile phone has cost hundreds of billions to develop over the years, if you think about it. Millions of people, very smart and all the rest, all working away. So why would you design one yourself? You just take one that's there, and because in a way all that space is doing is saying I could do it from here, or I could throw it 200 or 500 kilometers up and do it from there. So if you're not going out into the deep outer space, you're still protected by a lot of the Earth. Like the Earth's magnetic field is still protecting you. So you don't get all that cosmic radiation, which is really, and it's a little bit more, but you don't get the full whack of it. So if you're low enough, you're also protected by the Earth, this wonderful Earth that we live in. The use is almost limitless, and I'm not really going to go into that. By definition, it would take a long time to talk about a limitless conversation. But in 2017, India launched 31 payloads, looking a bit like this, from this rocket. In December, SpaceX, so this was India, but in December, SpaceX, which is a company, not a country, obviously, they launched 64 from one satellite. The intention this year is for over 100. They want to break the 100 barrier from one launcher. But SpaceX, India, countries, I should say, like New Zealand, are building, actually, technically they're not building the rockets, they're flying the rockets from New Zealand. In Middleton here, we have the National Space Centre. I don't know if any of you have, I don't know if you know it, and I don't know if you have visited it. Okay, so the National Space Centre is a really interesting place to look at. One of the things they do is they connect satellites to ground. What they were set up for originally really was to point at geostationary satellites, take TV down. So for example, TV from the Middle East would go up to a satellite, come down to Middleton, that would get brought by fibre to the UK, for example. Okay, that was the way it was done. However, in more recent times, what has been happening is a company called Rocket Labs, which is out of California, but are launching rockets like this. You can see this isn't huge. This isn't a massive big rocket. If I just go back for a second, you kind of get a sense of scale. I mean, I don't think there's a person here, but like a person is going to be, this is a person height, say, something like this. I know that's a window, but that's going to be something like a person height. So this is a huge rocket. This is clearly a lot smaller. And yet these are launching, 8, 12, 15 satellites at a time. Interestingly, they launch them from New Zealand over the Antarctic, and then it goes around, and the standard orbit brings it over Cork. The first orbit is over Cork. So the guys in Middleton are able to do some of the first contacts after you go to the Antarctic, and then you go around and you go to a place like Russia, and that you may not have any agreement with Russia, so you don't transmit to Russia. I mean, I'm not making a political comment, obviously. But when you come over a friendly nation, which isn't a member of NATO, for example, then you download, you connect. So interesting enough, just down the road, we're connecting to satellites that are launched in New Zealand. So the intention actually is, or the likelihood, I think you'll see an Irish satellite launched on a Rocket Labs launch from New Zealand in October. That's a bit specific, isn't it? Yeah. So anyway, that's our intention. So other big targets for new space. So one could go on all day. I want to pick one or two because I think one or two are interesting about this, about this future business. So there's a company which I haven't actually mentioned here directly, but called O3b, which is the other 3 billion. So there's basically 3 billion of us connected roughly to the internet, and 3 billion aren't. So there's a company set up to connect the other 3 billion, O3b. So I'm going to just say something about rural broadband in Ireland in a second. Okay, so just bear with me for a moment. But autonomous vehicles, they're the target of new space. So if you look at the likes of Elon Musk and SpaceX, and you ask yourself, you think to yourself, okay, he wants to go to Mars. He wants this company, he's mad, he wants to go to Mars and all that. Actually, he does. But that's not where you think he's making his money. That's not where SpaceX is making their money from. SpaceX is making their money from solving rural broadband, not in Ireland, but in bigger jurisdictions, and by setting up satellites that will control autonomous vehicles. Massive markets. In fact, although it's not mentioned on this slide, the internet that you use today, which largely comes through fiber or copper or stations that connect line of sight with each other, or maybe Wi-Fi, which isn't necessarily a line of sight connectivity, but all on the surface of the Earth. Think about our earlier comment about Neil Armstrong being the first person not to stand on the surface of this planet. All our internet, pretty much, not quite, little bit of it goes into space, but almost all of it goes through fibers and other devices on the planet. The prediction is that's going up into space. So this is why there are likes of Elon Musk and so on is really excited by this. So if you're a young kid today and you're using your device and you're thinking, why does this matter? It matters because in years' time, although you won't notice it, it'll just be still a device. It'll be through satellites. There'll be low Earth orbit satellites, they'll be flying over your head. You won't notice them, but they will be there. And it's a very exciting time to be alive in that sense. Here's just very quickly, here's a map of rural broadband in Ireland. Anywhere where you see purple is good news, anywhere where you don't is not good news. So, where is the purple in terms of percentage? Not great. Doesn't mean there's no, I'm just thinking of Limerick, depending on where you are, Limerick. But it doesn't mean there's no coverage, of course, but we all know there's issues with coverage. And there's certain communities, I was talking to a guy, we had him in here earlier in the week, I won't say one, but they've set up their own small local company for delivering broadband because they can't get it any other way. If you bring satellites to do it, well, this is an example of another company, because I just wanted to mention this, called OneWeb. If you think of the name OneWeb, each of these, I always think this is a funny diagram. I always think maybe I should change this when I use this diagram. Each of these is a spacecraft, each of these blue thingies, and you can kind of see that they show a cone coming out of it. So that's the area that they're communicating with the ground. And what you're seeing is, if you put up enough of these, you cover the entire planet. Does that make some sense? Yeah, in terms of diagram. Okay, one of the things that's interesting about this company, and there's my fancy graphics coming in here on the bottom left, and if you missed it, well, you didn't miss anything worth missing. But what OneWeb are doing is really interesting. They're taking effectively the view that if you make all these satellites the same, you can build them very quickly. So traditionally, we build a satellite and then we go to build another one and it's different. So we have to start again. It's all bespoke. If you've ever done anything in your home or whatever that's bespoke, you know just how much more expensive that is. It's the same as the Ford car. Why was Ford able to make cars so cheap? His famous comment, I don't know if it's actually true, I mean, I never double check this, but you can have any colour you like as long as it's black. So basically they were going to be direct replicas, and this came up with the idea of a production line. Today we all want something a little bit different, but the production line for the most part, 90% of the car you buy, whether it's the GT, DDD version or the is the same under. Why? Because otherwise it's not cost effective. So this is what people are doing going to space. They're saying, let's do what they do with cars. So OneWeb say, no one has ever, I almost want to do the voice, no one has ever built a satellite in one day. We will build several every day. Thank you. But in all seriousness, there's a bit of rhetoric around that, of course. But that is the intention by them, is to build stuff quickly, maybe every few days. They're still saying one day, I don't know, but they're still doing that. Coming towards the end of the talk, this is some of you may, if you go on the internet, Wired is a magazine of, I don't know, and now I realize how old I am. Is it a blog, is it a magazine? I don't know. It's a thing you can get on the internet. But this is from earlier this year. You can see, actually, it says it somewhere, anyway, but you can clearly see it, the number here, but there's somewhere it says it's January, I think, of this year. So 2019 is the year that space tourism finally becomes a reality. No, really. So clearly what the author is saying to you here is nobody's going to believe this. But actually space tourism is now becoming something, and it really is. So what could happen? There's various different things. I'm just going to go very quickly through them. So the first thing is, if you stick too close to the Earth, you can go up in one of these zero-G spacecraft, aircraft. So it goes up and it goes down like that. And when you go and it's coming down, you're falling with the aircraft, and therefore, relative to the aircraft, you're floating. You're actually falling, but that's what orbit means, by the way, as we'll just see in a second. So here's an example of some lady who's clearly excited by falling. So you can do this a lot of times. You do about 20 times, and you can pay money for this. The great thing with this is you just use fairly standard or slightly changed aircraft. Clearly no seats inside, but also they go slightly higher to give you that dive that you need. But you don't need any special training. It's pretty inexpensive. You can do it for a couple of grand, and in principle, it's scalable. You can lots of aircraft. However, if you want to go a little bit higher, and this is where a lot of the fun is, here's just something maybe again for students to get. I remember the first time I heard this, I thought that's really interesting. So you may have heard this before, but let me just say it briefly. If you fire something, now I admit here it's being fired sort of horizontally. If you fire it with a little bit of energy, you fall to A little bit more energy, you fall to B. Now we're going to see in a minute more energy, but just concentrate on those two first of all. While you're falling, you're weightless. Okay. Now, weightless refers to a force. Mass doesn't change. So your mass is always the same, irrespective, but your weight does change. So the weight is the apparent force that's acting on you. And when you're falling free, then if you're in, for example, you may have seen this, if you go into a lift, not do a lift, and you close, because the lift you can't see outside, and the lift falls, you don't actually know if somebody whipped the earth away from under you and now there's no gravity, or you're falling. You might know it at the end, but you can't tell. It's a thing called the Einstein's equivalence principle. So if you do this, then you can take the likes of what is going on in the Mojave Desert with Virgin Galactic, so Richard Branson's. So this is two spacecraft, you strap one underneath it, this is the thing underneath it, you bring it up to a certain height, then you fire a rocket engine, and then you do this. You sit inside and you go, oh my god, that is amazing. So this is from February of this year. I think this is the February flight. This is one of the test pilots, clearly hates his job, looking out the window, and actually you can see this is the Earth. It's upside down, but this is kind of the curvature of the Earth here. Actually, this one isn't upside down, but this is, you can see the interface between the Earth and the sky. Maybe it is upside down. I can't really tell now anymore. I'm not so sure. However, that's not the key point as to my confusion otherwise. But they're taking you up for roughly $250,000. So what they're really doing is just firing you, and then you fall back. And when you fall back, you get about 5 minutes of weightlessness. 90 minutes in total between the whole thing. And they've built this spaceport so that you get an end-to-end experience. So from the moment the moment that you go up, it's a real experience. Blue Origin are doing something different. So the guy who owns Amazon, who, if you saw him in the news, he was in the news last week because he had the most expensive divorce in history, and his wife got 35 billion out of the divorce settlement. And I happened to be away, and I was listening to CNBC, and they were commenting about, well, Bob, but she could have got so much more, and I'm sitting there in my hotel room thinking, okay, 35 billion, I get it, that maybe she didn't get as much as she could have, but I think she's probably going to be okay. And it was just a really surreal conversation about people, because I just realized how different their lifestyle is to mine, basically. But what's kind of interesting is Jeff Bezos, being more serious, owns Blue Origin. So he made his money from Amazon, still does, and he's retained the full rights to this, because he basically wants to send people into space. They're using a different approach to Virgin Galactic. This is actually a liftoff, and 7 minutes later touchdown. So they use the same rocket going up and coming down. Interestingly, no debris. So this rocket doesn't break into little different bits and pieces. So this is now moving towards this let's not pollute space, because people who want to go into space probably will want to be able to go back and say, I spent my amount of money and I didn't mess up the environment. So it's going to be the type of conversation you can have without people saying, you know, you're horrible. So there's this whole, but you have to think of the whole tourist experience, because that's where we've moved, appropriately so. But what's interesting is, and it may not be so obvious, you can see these black things here. These are large windows. So they basically say, well, if you go up into space, you don't want a little portal. So if you go back to this guy who clearly is having a lot of fun, he's nevertheless looking out at something which is a bit smaller. And you know the way if you're in an aircraft, you're always trying to just see the bit that you can't see. It's kind of a human condition. So if you're being serious about space tourism, then this is the way you operate it. If you fire things a little bit faster, then you do this. Instead of going A and B, you get into a similar state, but your falling misses the Earth. So there's that thing about in the Hitchhiker's Guide to the Galaxy about throwing yourself at the ground and missing. That's what going into orbit means, and effectively that's what it is. So it's the same thing, but instead of hitting A, B, you hit C, but actually C means that you never actually hit the surface of the Earth. This is the big deal. This is going into orbit. Once you're in orbit, you can stay there for a long time. So up to really everything we're looking at the minute, and let me try to finish very quickly. Everything we're seeing at the minute is really about this A and B, the few minutes, because if you go into orbit, it's horrendously expensive. Dennis Tito was the first person in 2001. It cost him 20 million. He went to the International Space Station. Greg Olson in 2005, there's been 6 people. He's reportedly spent twice that to go to the International Space Station. But this is clearly a playground for people who are incredibly rich. But the other thing about it is this isn't really a tourist experience in the strict sense. I mean, from my perspective, here's the thing. I go up to the International Space Station and I go on board, and I've got all these people who are highly trained who are working. And I'm there saying, whoa, let me have a look at this. You know, I'm in the way. Okay, the only reason I'm there is because I have 20 million. It's not really a tourist experience. They don't want me there. I'm not doing anything constructive. To me, it's a horrible use of your 20 million. But that's obviously clearly not what Dennis Tito and Greg Olson do a billions thing. But in terms of a market, it isn't really. Most of us want to feel like where we are, we're not in the way at least. Going around the moon, there's a Japanese billionaire called Yusaku Maezawa. He wants to take 7 artists with him and go around the moon. SpaceX say they'll do this in 2023, possibly. You saw last night the Israelis attempted to land something on the moon and got there and got some nice pictures, but the last bit didn't go so well. If you're going around the moon, it's a lot easier. So that's why going around the moon is probably something we can do. Going up and going around and landing on the Earth, because the atmosphere slows you down. There's no atmosphere to slow you down on the moon. Plus, there's a lot of ocean on the Earth, so 80% is ocean. So, you know, there's no mountains in the ocean. There's no craters in the ocean. On the moon, there's mountains and craters all over the place. So it's much safer to go around the moon and then land back on the Earth. But you may have seen the American vice presidents committed NASA to going back to the moon by 2024, so 5 years time. And the tweet from NASA was challenge accepted, which is definite, which is great, because that's really what you want to hear from NASA, not which is probably their thinking. But I know that back in 1962, when John F. Kennedy, if you've ever heard his speech from Rice University, you've all heard the famous one, we choose to go to the moon, not because it's easy, but because it is hard. If you've never seen, honestly tonight, go on Google, John F. Kennedy, Rice University, you won't even have to put moon speech or whatever. It'll send shivers up and down your spine. It does mine every time I hear it. It's incredible, that sort of sense. But one of the things he said, by the way, is about sending, now he does say a man, think of it as the 60s, okay, so just ignore that commentary now. We're actually more likely to send women for all sorts of reasons, physiologically as well as everything else. But at that time he says we choose to send a man to the moon and return him safely to Earth. And the key thing is, back then he even saw the importance of safe travel, not just going there for the sake of it. He realized and recognized, and I think he fundamentally recognized, the importance of being alive. It's great to explore, but life is really precious. So when we're exploring, let's protect it as best we can. So the challenge was to make sure that you would bring people back safely. In fact, the reason why the Apollo program was cancelled, there's two reasons. One, kind of fell out of public favour. By Apollo 17, people didn't even hardly know we were going to the moon. But secondly, as we've learned in more recent years, NASA engineers were saying this is going to go badly wrong sooner or later. This is really high risk stuff. We've been so lucky. Remember, Apollo 13 was almost a disaster. And so they decided to cancel it because they realized the technology wasn't really mature enough to keep on doing this regularly. The idea now is we want to do this regularly. But here's the thing that I think is interesting. We talk about the impact on our society and talk with kids about this. Even the Americans are saying we'll work with anybody, private companies, other countries, except China, incidentally. Interestingly, at the moment, China is the one country the US will not work with in space. But they'll work. That may change. But at the moment, the NASA are forbidden to work with the Chinese. But they will work with Irish companies. They'll work with anybody. So we could really see an interesting opportunity for Irish companies to get involved in this. Alternatively, you could consider going to Mars. But the United Arab Emirates have put in this, are building. This is an artist's impression. Are building a Martian environment for two reasons. One, they want to get young people excited by the prospect, and therefore go on to spend time on Mars. But secondly, they want to be seen to be, and by the way, the reason they need to do that is because they realise, as a country, and it's a fairly obvious statement, that the fossil fuels is going to run out. They're great for photovoltaic, obviously, they'll have that, but they need other things to drive their economy. So they need people to be interested in innovation and STEM, and astronomy is a great way to catalyse that. So they're intending building this big village. So what was interesting is, this is from January of this year. I think it's cut off, but it's from the Emirates Woman magazine, which I think is interesting. And it says, want to go to Mars without leaving the UAE, you might be able to ... So that might sound past remarkable at me, but think of the context that a society where women are considered to have a certain role in this society, which is more restricted. We would consider quite restricted. I'm trying not to pass remarkably about other people's cultures. But what's interesting is that they're trying to get everybody to think about the possibilities of any gender. Finally, a couple of quick points. If you have 100 grand, build your own satellite. Actually, if you have about 10 grand, build your own satellite. You need another 80 or 90 to launch it. But if you have 100 grand, not a lot of money. I mean, it's a lot on a personal level. It's not a lot of money. You can build and fly your own satellite. Where would you do it from? Well, you do it from New Zealand, of course. So as we show, here we show New Zealand, except we didn't. So we're showing couple of arrows. One is where the UK is building their spaceport. So if you don't know this, in Prestwick, the UK intends to launch satellites in a couple of years' time. So they'll have an end-to-end system where you can build your satellite there and launch it all in one go. It turns out that you could launch satellites from Ireland. Now there's no plan to do this at the minute, but it's not crazy. Why is it not crazy? Actually, Ireland is a better place to launch a satellite from. If you look at possibilities of crashing if you're launched from Prestwick, if you actually take the southern coast of Ireland, and there is a reason, by the way, why you launch slightly west. That's actually the angle you want to do. It's for what's called a sun-synchronous orbit. So it just turns out that being on the western side of Europe is the perfect place to be if you want to launch satellites. You can launch them northwards, you can launch them southwards. So will somebody do that? I don't know. But it's not mad any longer. And if you think about smaller rockets with smaller satellites, more cost effective, maybe there's a kid who we're dealing with will actually think, I want to do this, or I'm going to be part of this. Who knows? I don't know. But what I think is really nice is in this 50th year of anniversary of setting foot on the moon, we've gone from the participation being essentially by a monolithic superpower to the potential for us to launch useful things from rural communities in Ireland. That's how much things have moved on, and I think that is really fascinating. finally, did I say finally before? I do that. I forget. I should look at my slides here. But finally, just you know what? Actually, here's the thing. Do I have a thing? Yes, the only effect. So I'm going to finish with this slide. I think there's one more slide, but I'm going to finish with this slide. We hear, because this is something that I just got to say. Okay, so I've learned, you have to say it, just say it. So we hear a lot, and we hear a lot of things like, for example, going into space and looking down on the Earth, and how that will have a transformational effect on you, because you will see the planet below you. We know that astronauts say this, and they call it the overview effect, because you're getting clearly an overview of your planet. But I wonder sometimes, have those same people ever really gone out on a really dark side? And maybe they have, I don't know. So I'll be honest on that. But I'm going to tell you how I feel. If they go out on a really dark night, and they allow their eyes to become dark adapted, and they look up at the majesty of the heavens above, if they don't feel fragile by doing it that way, then I have no idea what way their brain is wired. You don't need to go up to look back to appreciate the Earth, in my view. So I like to use the phrase the underview effect, because you just need to go out, and if one has an opportunity to take groups out and just look up with your eye, no telescopes, no binoculars, 20 minutes of allowing your eyes to adapt to the dark. Get a little bit away from city lights as far as you can. We have some amazing locations in Ireland, but you don't necessarily have to go to the amazing locations. And you can stand, you can sit, you can do what we used to do when I was younger. Haven't done it in a few years, maybe I should. Get into the sleeping bag with a bunch of friends and just chat and look at the sky above you. You will now see satellites every so often. It doesn't have to be the International Space Station. You will see meteors, which will just flash across the sky. You'll see stars twinkling. Maybe you'll see planets. Maybe you'll see, depending on where you are, the northern lights. That's more rare. All the other things you will just see by default. And when you realize that that is an enormous universe, and you're here looking at that, and most importantly, you're able to do that. And you maybe think, I remember there was some guy in this castle thing back in Cork, told us about how the Earth got formed, and the Earth-Moon system, and a small bit about that. And when I'm looking up at this guy, he never told us what those points of light were, so that's not great, because I didn't. But that you might remember that just the share the enthusiasm, and I'm saying this very badly, but share the enthusiasm of just being, of just existing. When we talk about what does astronomy teach us, I've done some exciting things, but actually, or things that could be exciting or commercially viable, but actually one of the things it just teaches us is how lucky we are to exist. And actually that's the most important thing. It's taken me many years to really realize that, but that's the most important thing astronomy teaches us. It teaches us that we're on a tiny planet, that we have the capacity to understand the universe around us, which is amazing that we have that capacity, and to enjoy it. And to share that with others is one of the best things that we can do. So when we think about tourism, dark sky tourism, when we think about where is this going, what is the societal impact, there is one that's free to all of us, and it's going out and just looking up at the dark sky. Anyway, I could wax very unlyrically for hours on that. I won't. I will leave it so that we can have questions if there's any, or comments. None of you fell asleep. Thank you so much. That's really appreciated. But that's all I was going to say for tonight. I have no idea how long I went on. So my apologies if it was longer than I intended. But anyway, thank you. And if there's any questions, please, we have some questions or observations or comments.